quite a long time. The settling velocity is quite small. I have to switch this on here again because I had a comment that now the recording is going on. So, and all particles larger than 100 micrometers are named droplets because then we have this pretty fast settling of the particles and they don't follow the flow motion anymore. So in medicine, on the other hand, all particles larger 5 micrometer are, let's say, considered as droplets. And they teach in medicine also that the particles larger 5 micrometer fall down quite quickly and they do not follow the flow. So this is wrong, but they teach that. And now the important aspect is that when you believe that these particles are behaving like droplets, then smear infection is something which is quite serious. So you have to develop protection measures against smear infection. And that's what they did at the beginning. And then the people were saying wearing a mask is very good because then you are not doing all the time the face touching. But the problem is that these particles are airborne, and that's why smear infection is not so much of a problem. It's, let's say, the inhalation of the particles. And there's a nice article about this controversy. So if you are more interested, please study that. So because of this little problem, and of course it cannot be solved, I thought it would be better not to talk about droplets and aerosol particles. It's much better to talk about the direct infection and the indirect infection, because that makes it more clearly also what kind of safety measures you need. So what is a direct infection? So the direct infection takes place when people are nearby, let's say 1.5 meters or less. And then, of course, aerosol particles, so the little ones here, and droplets are emitted by the infected person, and then this person can inhale aerosol particles and droplets as well. And so most of the time, the number of aerosol particles is much larger. So even over short distance, the biggest problem is coming from the aerosol particles, not from the droplets. So of course, you can raise the distance, you can use a mask and so on to protect yourself from a direct infection. And then there's the indirect infection, meaning that the full room is, let's say, contaminated with tiny little aerosol particles with viruses. And so here we don't have the droplet problem, it's only indirect infection. And here distance doesn't matter, so you cannot protect yourself by raising the distance to person or to people because the full room is contaminated. So you need other safety measures in order to protect yourself from indirect infection than for a direct infection. And that's why I like to talk about today about the possibilities of masks in view of direct and indirect infection, protective walls, mobile air purifiers, and I will probably move the application section into the discussion section to measure the timeline before I come to the conclusions. So let's talk at first about masks. Of course, at the beginning of the pandemic, the people were saying that the masks are not very helpful. That's different now. They are recommended, but I would like to show you now that it's not so simple. And I also like to show you why these masks help. So at first, you see here a person speaking. And here we see a measurement, a PIV measurement of the flow. And now, of course, when the person is speaking or coughing or whatever, then of course also some aerosol particles are transported from the body into the air. And of course, these particles are moving with the flow. And that's why it's important to study the flow motion around the person. And you can see here that the flow motion during talking and breathing is, let's say, in a quite narrow area around this person, so let's say 0.5 meter or so, and then the flow is more or less at rest, meaning that most of the particles will stay here in this region and then they will lift up due to convection. So this means that when we are 1.5 meter apart from that from an infected person and we are simply speaking, we are pretty safe. So we will not infect each other when we are, let's say, talking for some time, 15 minutes or something like that. So that's why this general safety measure about distance is very helpful. So what's when we are coughing? So then you can see that, let's say we have now the flow motion going, let's say around 1.5 meters. And that's just a single curve. So when you're doing it more often over a longer sequence of time, then of course it can also reach larger distances, let's say 3 meters or something like this. So when a person is, let's say, doing irritation coughs, then please raise the distance. That's my recommendation. But on the other hand, you have to also keep in mind that these kind of events are not taking place so often, and even more seldom is sneezing. That's why I think sneezing is not so much of a problem during this pandemic. It's simply too seldom. But even here, you can see when you are 1.5 meters apart from that person, you are also pretty safe without any protection. So now, what's the advantage of a simple mask? So this is a simple surgical mask, and you can see when you are coughing now with the mask, the motion of the flow is restricted to the area very close to this person. So when you are wearing even a very simple mask, you are very well protecting other people when you are infected by yourself. So they protect others from direct infection in this case. But there is a problem, and you probably all know this problem. That's because the simple masks are not sealed. And then when you are talking, you have the advantage that the viruses are not spread into this direction here, but of course, all of the viruses are getting out. And that's simple fluid mechanics. Because of the gaps, most of the air is going through the gaps. And that's why all the particles are coming out here. So in particular, when you're sitting side by side, this mask is not very good because the particles are getting out sidewise. That's why these are very good for face-to-face conversation when you're doing shopping and so on, but of course not in a classroom, not in an office and so on, and not when you want to protect yourself, because you are not protecting yourself with this mask, because when you inhale with this mask, all the particles will also, with the virus, will also enter through the gaps. That's the problem of these masks. So that's why you have to wear better ones. And what means better? So we have tested a lot of mask materials, and I just want to show you 2 mask materials here now. So it's a little fluid mechanics experiment. So we have here basically a channel. The flow is going from left to right. And here at the inlet of the channel, we have some filter material. And then the area where the filter material is located is illuminated with a laser light sheet. And we have a camera here to record what's going on before the filter material and behind. And when we provide some particles here, we can see if they are going through the filter material when we drive our channel here. So that's actually the experiment. And you can see here now the filter material, top view, left before the filter material, right behind the filter material. And this shows you how it looks like for a simple surgical mask. So these masks do not filter. The intention of this mask is to block the flow and to filter big droplets and so on, and let's say something coming out of the mouth. But it's not against aerosol particles. So even if you seal this mask completely, they will not block the particles because they will go through the filter material if you do that. Anyhow, if you are going now to a good mask, which is N95 or KN95 or FFP2 in Germany, then you can see we have here the tiny little aerosol particles, 0.4 or 0.2 to 2 micrometers, and they go not, or just a few go through the filter material. So they filter very well. So if you want to protect yourself, you should wear these masks, and then you also protect others very well, because you don't have a gap flow. They seal very nicely. All the air goes through the filter material, and the filter material filters very well. So that's why you can use this mask. And if you use this mask, I would say that that's enough. You will not infect each other. So keep a bit the distances, and that's it. So quite simple from my point of view. But now we have to go a bit further into the physics of this mask. So why do they work so good, and why do other filter materials are not working very well? So we have here a random distribution of some fibers. And of course, now when a particle comes, then of course it can go through the fiber material here. unless, let's say, the particle is larger than the filter, the distance between the fibers. So if you have more and more filter material, then of course it's getting thicker and thicker, and it's more difficult to breathe. But it doesn't mean that the filtering gets better, because when the pore size is too large, then it will not filter. And that's what often is the case for normal material. So you can use big, thick ones, but it will not filter. So you need the right ones in order to filter it out with this method. But when you have small particles, this method is not working at all. So you have to use something else. And here we are considering now a single fiber and what's happening when particles of different size are coming near this fiber. So first, the flow goes around the fiber. We have here the streamlines, and we assume now that we have a small particle here, which is not blocked by the filter material at all. But we assume that this has still a certain size with some mass, so that it's not following the streamlines perfectly. And in this case, of course, when we have the curvature of the streamlines, the particle will not follow this curvature, and then it will come in contact with the fiber and it will stay there. So this is a typical inertia effect, which is quite essential, of course, for filtering. But when the particles are getting smaller, they will actually follow the streamlines. But in this case, it can be that the streamline is very close to the fiber, so that then, because of the size, they will be in contact, and then this particle will stay there. So that's another effect that can take place, interception effect. And of course, when the particles are even smaller, then we have something like the Brownian motion on top of the regular mean motion of the particles. And of course, in this case, the particle can also cross the streamlines, as you can see here. And that means that the particle, even when it's a bit further away and very tiny, it can get into contact with the fiber and then can be separated. That's the diffusion effect. And finally, when the particle is very, very tiny and far away, there might be an, let's say, an electrostatic interaction, so that also these particles are getting to the fiber and are separated in this case. So that's basically are the effects taking place. And now we have here the graph where we see here the particle diameter, and here's the separation efficiency. And you can see when you have a particle, let's say 1 micrometer in diameter and larger, then the inertia and the sieving effect start to work quite well. And let's say 10 or 50 micrometer particles are, let's say, separated by 100%, no question about that. So that's an easy task. That's why filters are usually pretty good in view of the larger particles. But this method fails for the smaller particles. But here now we have the, let's say at first here, the interception effect. So you see basically how well this works, and the diffusion effect basically. And basically the total separation of all the different effects gives the curve like this. So it's usually around 100% separation for the larger ones. It's close to 100% for the small ones, if the flow velocity is small enough. But here we have the little gap where it's not working so well. But you can see if you make it properly, you can still reject close to 100%. It's not a problem. So filter material are pretty good in this case. But this, of course, has to be known. And based on this analysis, we can say, of course, that the surgical masks are good because they block the forward distribution of the particles, so they protect others from a direct infection, but they do not protect yourself from indirect infection, so they do not offer any self-protection. FFP2 masks and so on, they protect yourself and they protect others from direct and indirect infection. That's why I think a mask is usually the best you can do. But, and this is now the main problem, these masks are not very comfortable, so you cannot wear them for long working days. So when you stay in a room for a long time, let's say for working, for school, or whatever, then you cannot wear this mask. So then the question arises, what can you do on a long run? So, and now I would like to tell you something about the protective walls. So you can see here the typical protective walls you can find in all shops, basically transparent perpex side wall. And now you can see what's going on when we are sitting here and a person is blowing some aerosol particles. So you can see basically that we have some blockage of the wall, of course, works quite well, but over time, some particles are crossing the border. Of course, the concentration will be lower. There is already quite some turbulent diffusion, so the risk of an infection here is much lower than without the wall. But of course, it's not perfect. So when you're working in fluid mechanics, of course, you know that you can make it better when you have, let's say, a little edge here around this side wall. And of course, when you repeat the experiment, then you can see that here is a vortex formed, and then more of the particles are staying on this side. So you can, let's say, decrease the distance to a person when you use these kind of protective walls, and then you can protect the people from a direct infection. And of course, these walls are used in all shops, as you know, but also in some schools. So you can see them here. So the kids can sit next to each other. They can talk, they can cough each other, they can laugh. So no problem at all. Direct infection will be minimized with these walls quite efficiently. But of course, the problem is that over time, of course, the aerosol particles will occupy the full room because the walls only protect from a direct infection, not from indirect infection. And that's why, of course, indirect infections can take place even when you are when you are using this kind of transparent walls. So what can we do against this kind of indirect infection? And I'm not now coming to the mobile air purifiers. So what is a mobile air purifier? So it's basically nothing else than a device like this, where you suck the flow through a pre-filter, which filters out large particles and dust and so on. Then you have the fan, which accelerates the flow through, let's say, kind of HEPA filter. And the HEPA filter uses all the effects I have outlined before. So these ones are really good, and they will basically reject all the tiny aerosol particles and viruses and so on. So that's basically what they are doing here. And then, of course, the filtered air is getting out here at some place. So, of course, if you have a HVAC system or air conditioning system in your room, you don't need that. But here in Germany or in Europe, we don't have this system usually built in our houses and public buildings. So that's why the question arises if we can use devices like this in order to protect the people in the rooms. So, and we have studied them quite a lot in the past. And the first question is, of course, when you install such a device in your room, if it becomes windy in the room. And you can see that from the PRV measurement over here, that let's say in a distance, let's say up to 50 centimeter of 500 millimeter from the device here next to the floor and here in this region, we have a significant flow velocity, but further away, we are below 0.25 meter per second. And this is so low that you don't feel it anymore. So when you bring such a device into your room and you operate it properly, you will not feel the airflow. So that's not an issue, even if some people are complaining about that. So the first investigation we did was performed in a kind of a classroom configuration. So in view of the size, so 9 by 9 meters, square meter. And we have here the location of the air purifier, and here another one, just to check the effect of the position. And then we have here different measurement location. And basically what we did is, you can see here the laser light sheet going through the room at some locations, or 2 locations. And here at the different location, so measurement position 6 and so on, we have installed a camera. And then the full room is contaminated with aerosol particles. And then we just measure over time the decay of the aerosol particles in the field of view. And basically, what you can see them is something like this. So this is just the recording over 50 minutes. And then you see over time that basically the number you can measure is decreasing. And then, of course, you can count the particles and normalize it with the initial number. And then you are getting a plot like this, basically. So this shows you the normalized particle image counts over time. So basically, the decay of the concentration when the air purifier is running. And you can see the quite nice or quite fast decay at the beginning. And then, of course, it's getting flat here. But here the concentration is so low that you may say it's not very dangerous staying in this room because you need quite a number of these viruses in order to get an infection. So how does this compare now to a room where you don't have any air purifier running? And that's the reference line over here, that's the red one. So then, of course, it decays a little bit because the room is never fully sealed. Some particles may also get in contact with the walls and so on. And that's why you have a little decay over here. But of course, if you stay in such a room for some time and the aerosol particles will be contaminated with the virus, you will be ill after some minutes. While here, you can stay for quite some time before getting infected. So this is now a list of the different measurement locations for different volume flows of the device and for the location A and the location B. And I will not go into the details. I just want to point out that when we go to this one here, we can see that, let's say, the air exchange rate, so the number of air exchanges per hour given by this number here, is pretty constant for all measurement locations. So that's maybe quite surprising, but you have to keep in mind that you always have some turbulent mixing in these rooms, and therefore you have always a nice mixed situation, and that's why you don't have any areas in the room where the particles will remain for a long time. And in others, they will disappear quite fast. So it's pretty equal in all areas of the room. So don't believe the statements that in some areas you might find much more than in others. You can see here 10% variations or 15%, but not more than this. And the second interesting point is now when you compare position A to position B, you can see when it's located in the corner, then it's reduced. It's getting less efficient for all measurement locations by about 20% or so. And this has basically two effects. The first is, of course, basically the position is not that great in view of access to the aerosol particles. But there's something more, and that's the lamp at the ceiling, which was located here. Not a single lamp. So these are lamps going through the whole lecture room. And then what's happening is basically that the clean air is going to the ceiling. Then usually it follows the ceiling, but when you have a lamp here, then you are creating a vortex. And this is now essential because it's very important for the air purification that the clean air can, let's say, follow the ceiling until the end wall of the room, and then it goes down. So that's basically how these devices work. And when you block this kind of flow at the ceiling with some obstacles, then the performance goes down. And that's what you could see in the table before. So when you install these kind of devices, look for an area where the ceiling is free from obstacles. And then you can make sure that the performance works quite well, because this is, let's say, not optimal when you have this kind of recirculating flow in this area over here. But on the other hand, you could see, even if you have these kind of side effects, you can easily compensate that by in raising the volume flow slightly, and then it's working again quite well. Okay, that's about the importance of the ceiling. Ceiling must be as clean as possible. And now what's about objects in the room? So we have now, again, the same room, but now the room is occupied with chairs and tables. We also have the transparent sideboards here between the chairs. And we also had people with jackets, laptops, and so on in this room. So the air purifier is placed over here, and the measurement location is quite far away, you know, to see the worst behavior in this room. You can see now the result. And let me outline this in a bit more detail. So again, we have here the time axis. So you see the typical decay here. And here the black dots, that's basically the decay when you're not doing nothing. So that's a natural decay due to the leakage in the room. So now what's happening when we open the doors of this room, which represents some window ventilation, and then you can see it looks like this. So of course it works, and but sometimes it's worse better than other times. So window ventilation you know, depends on temperature gradients, on wind conditions outside, and so on. So that's a little problem. And now, in contrast to this, we have here the air purification with an air purifier, so much more efficient than the window ventilation. And we see now green, red, and blue dots here following on top of each other. So what does it mean? So the green ones is a room without any people and without the barriers, just the chairs and the tables. Red means with people, but no transparent side walls. And blue means with people and with the transparent side walls. And you can see from this figure, it doesn't really matter what you are putting into your room, because filtering doesn't depend on the object in your room, basically. So in particular, when you have people in the room, that's usually quite good, because they are breathing, they are shaking with their hands maybe, they have the thermal convection, they produce the thermal convection, and all this enhances the mixing. And I already told you that mixing is good for filtration. So that's why having people in the room moving around and so on is quite good, and not a drawback, as some people speculate. And you can see, even when you have these protection walls, they do not hinder the filtering at all. And of course, the filtering is done in a continuous manner here, while the recommendation about the window ventilations are just, let's say, the short-term ventilation. And what does this mean? So let's go back to these curves over here. So if you open the windows, let's say for about 3 minutes, and then you close it again, then of course, from the initial value of the concentration, you will reject some of the particles, but then the particle concentration will stay quite high again. So the infection risk is really high if you have just a short period where the windows are open, and then the ventilation is maybe not working so well. So that's the problem of the short ventilation period, basically. So when you have air purification, and let's say the rejection of particles is done continuously, you know, you have much better conditions usually in this kind of rooms.
So Christian, try to come to a close in 5 minutes.
Yeah, just a few more slides before I end up.
Thanks a lot.
Sorry. So now you may say, this is not the realistic conditions in practice, because there we don't have a contaminated room. The contamination is basically built up. And that's why I like to explain you this now here at the end. So we have here the 45 minutes, and here we see the virus load in the room, basically. And let's say if we have an infected person, then of course the virus load increases over time. And of course, the virus load depends on the source, so the number of people, their activities, of the infected people, of course, only. And it depends on the size of the room. So very large room, of course, you cannot generate a large virus load. So in a church, it's completely safe normally because the volume is so large. But anyhow, that's how it looks like. And now we can let's say, draw here a line, meaning this is a mean virus load over time, basically. We call this here 100%. So now let's consider a 3 to 5 minutes shock ventilation, what is often recommended. Then of course we have the increase over time. Then we can hope that during the shock ventilation we are rejecting all the particles and viruses. And then when we close the particle and the infected person stays in the room, we have the race again. So in this case, we can reduce the virus load by 50%. That's the best we can gain. And only if we go from 100% or close to 100% to 0 here in this case. But of course, this is not possible in practice, as I showed you before in the experiment. So normally it's going down a little here and then raises again. And then you have a reduction of the virus, which is much, much less than this. So in contrast, if you use, let's say, a mechanical device for the rejection of the particles, then of course you have also some increase of the virus at the beginning, but then it stays on a constant level. And the location of this level depends basically on the volume flow of your air purifier and the filtering capabilities, basically. So how well your tiny little aerosol particles and viruses are filtered out. Okay, but it's important that these air purifiers fulfill 3 criteria. So they should, the volume flow should be large enough so that they can filter at least 6 times the room volume per hour. So this is now worldwide more or less a recommendation. They should use quite good filters because they filter very well, but then it's also guaranteed that they don't have any gap flow because this is also, let's say, specified how they have to be integrated in the system. So if you operate poor filters, they usually have also quite large leakage flows. And then the discussion with the surgical mask holds as well for the simple filters. So I would recommend to use the good ones. And they should be not so loud. So because when they are very loud, you are switching them off and then they are not helpful anymore. So 50 dB or less is something I would recommend, but you can also buy devices for 40 dB or less. So you can always match your dB criteria by number of devices. So if one is too loud, you can install 2 with half the volume flow, and then they will be much more quiet. Anyhow, you have to pay for that. So I will skip the application section and I come directly now to the conclusions of what I've outlined before. So remember the surgical mask we have tested, they protect others against direct infection, but they do not protect yourself basically because of the leakage mainly, but also of the poor filtering capabilities. So use good masks, they will protect against the direct and the indirect infection. And of course, they provide self-protection, but also protection of others. And now the people are usually saying that not all people are able to wear this mask correctly. That's right, but it doesn't matter. If 80% of the people are able to wear this mask correctly, then 100% of the people are protected. So that's not an argument from my point of view. I think it's always better to use these kind of masks. Of course, you cannot wear this mask all the time, in particular not when you are sitting in a lecture room for a long time, in a classroom or in an office. So you need something else. And here we would recommend, based on our research, these kind of protection walls with a perimeter edge to create the little vortex, which keeps the aerosol particles and the viruses on the side where they are emitted. And then they can prevent people nearby from a direct infection. That's why it's very useful using these kind of protection walls also in supermarkets and so on. But of course, they cannot protect from indirect infection. Here you can use mobile air purifiers if the volume flow is large enough and they have a good filter. Of course, if you have a HVAC system in your building, use that. That's even better, because these systems are not operating based on mixed ventilation, and that's why they are even more efficient. But unfortunately, if you don't have them, that's our recommendation, basically, to still use the room during the pandemic and to come back to normal. Okay, so advantage, as outlined before, they are much better than shock ventilation because they operate all the time. They have a much larger volume flow than the window ventilation, usually because they do not depend basically on temperature differences, flow outside, so wind outside. They are not making the room cold, windy, and they are not wasting the energy as window ventilation. That's why we are recommending these kind of devices in combination with all the other safety measures we have outlined before. So with this, I would like to thank you for your attention. Thank you. Sorry for let's say for overcoming the time here a little bit, but hopefully enough time for some questions. Thank you very much.
Thank you.